As an example, consider a bar 12 inches by 1 inch that's subjected to two forces. So we have a 2-pound force acting in C and a 2-pound force acting in A. The force in A is going up and the force in C is going down. And let's find the resultant force and moment, first in A and then in B. So the resultant force and resultant moment in A is the sum of the forces first for the resultant, so that'll be 2EY minus 2EY, and the units there are pounds. I'll leave the units out, we'll fill them in at the very end. And the resultant moment in A is the lever arm, which is 0 to the first force, so that's 2EY, plus the lever arm to the second force, so which is located in C. So that one is 12EX plus 1EY cross product, and the force is minus 2EY. So that's the moment from the second force, the one in C and the one in A. So out of the first term here, I'm going to get 0 because 2 minus 2 is 0. And then when I look at the resultant moment, the first term, the force in A, is going to give me 0, and then out of the second term I am going to have EX cross EY, and then I'll have EY cross EY. EY cross EY is 0, parallel vectors, cross product is 0, and EX cross EY is going to give me EZ. So out of this I'm going to get minus 24 EZ, and the units here are pounds inch. So that's the characterization of the force system in A, and so if I'm going to draw that, I can draw my system. There's no net force in A, but there is a moment of 24 pound inches, or inch pounds, depending on how you want to say it, both equivalent to each other. I can also do the characterization in B, and in principle this should give me something different. Well, the sum of the forces is going to not change with the reference point, but with the change in reference point comes a change in the lever arm. So first we have the force at A, and the position vector to it is minus 6 EX, cross product with 2 EY, and then the position vector to C is going to be 6 EX plus 1 EY, cross product with minus 2 EY. So the cross product out of the first term is going to give me a minus 12 EZ, and the cross product from the second term is also going to give me a minus 12 EZ. So altogether, I'm going to have 0 minus 24 EZ pound inches. It's important to keep track of the units. So if I were to draw this pictorially, I have point B here, and the force system can be drawn as 24 pound inches there. So you'll notice something special about this problem here. I changed the reference point from A to B, and my resultant expressions didn't change. So this is a special case here. So there are a couple important remarks here. First, if the resultant force is equal to 0 in your system, and the resultant moment's not equal to 0, the force system is called a pure couple system, or simply just a couple. And couples are special. And in particular, in a pure couple system, the resultant moment is independent of the reference point. So I can put whatever reference point I want, and I've always had the same expression for MR. So that's something unique about pure couple systems, and those are systems where the net force, the resultant force, is equal to 0. Just as a bit of terminology, we can also talk about the flip case. So if the resultant force is not zero, but the resultant moment is zero relative to, say, a given point A, then the force system is called a point force system in A. So these are two special cases of force systems that are useful to know about.